Hello, everybody. I'm Milos. I'm currently a fourth-year PhD student. I'm from Slovakia. This is the logo of my university from the eastern part in Košice. My academic supervisor there is Dr. Karel Saxel, and my ILO supervisor here is Dr. Marek Fejercak. And I'm dealing with thermoelectrics materials, but today I will speak about the simulation, computer simulations, namely molecular dynamics and Monte Carlo simulations. So starting with the first one, let me invite you to a party. And at this party, we can see the people dancing, and they creating so-called long conga line dance. And as we can see, they are touching each other, creating a trajectory. And some people are happy with that. Some people are not. Some people don't even care. But our question is this a good party? One way we can find it out will be to ask one of these dancers and interview him and ask about his time averaged impressions. But we don't know if this dancer was able to dance over the whole circle. Another way to finding about this party will be take a photo of each of these dancers at the same time, and then count the number of happy and sad faces and make an average of them. And after that, we will find out like this party was, let's say, good. This is a very simplistic way how to show you what the molecular dynamics is about. In a real molecular dynamic simulation, these circles are representing a state of a system. A system is a set of atoms or molecules we are interested in. And we'll basically let this system evolve in time. So each of these states are connected to each other, creating some kind of trajectory. And if we let this system evolve enough in time, it will basically get to each of these states. So, and if the system will be in equilibrium, we can call him ergodic. And this is the fulfillment of ergodic hypothesis. So we can ask about some property of the system, not by measuring this property as a time average, but as an ensemble average. An ensemble is a term from statistical mechanics describing a configuration or set of configuration of some particular atoms or molecules, and according to their distribution function, and we call it as a statistical ensemble. This ensemble is controlled by a set of parameters, a small set of parameters, thermodynamic ones, and we can have, for example, NDE ensemble. These parameters are constant for this ensemble. So the number of the particles, the volume of the simulation box, and the energy of this ensemble will be constant. So we can call these processes as adiabatic, and this molecular dynamic simulation will change its trajectory by changing kinetic energy to potential, but like the total energy will be conserved. Another example is NVT ensemble, so with constant number of particles and volume and the temperature. So now we introduce a thermostat, and we allow exchange of energy with this thermostat for, like, say, endothermic and exothermic processes. The kinetic energy, or the average of a kinetic energy, is linked to temperature by this equation, but this is only the average energy, and like instantaneous kinetic energy can change with the velocities of our particles, of course. The third example will be the NPT ensemble. So the particles pressure, in this case, and temperature will be constant, and we can change the we can resume this pressure to be constant by changing the volume of our simulation box. So these two examples. So let's go back to computer simulation. We call a computer simulation a molecular dynamic computer simulation a technique which let some system evolve in time and create some trajectory. And we basically then integrate this trajectory using classical mechanics equations and indeed Newton laws. Computer simulation can serve as a bridge between microscopic time and length scales, and we can make predictions to macroscopic or bark properties. Computer simulation as well can serve as a bridge between the theory and the experiment, when we can test our theory by simulating a model, or we can compare then our model to some experimental results. So as well, what is important on computer simulation, we can create some experiments which will be not possible or very difficult in our laboratories. So for example, if some substance is very expensive, or if you want to simulate something under a very high temperature or high pressure. So let's build a model of this kind of molecular dynamic simulation, starting with the ensemble. So we take one of these, let's say MBE ensemble. This is the first step of our model. And then we'll need, as I said, some basic Newton equations. So second Newton law, the first derivative, time derivative of position vector will be the velocity. Then the second will be the acceleration. Let's assume we are talking about molecules. So there are interactions between them. Let's say we are forming some potential. And this potential will be a function of like a many-body function of all of these positions of molecules in this system. And if we say that this potential or this force field, we will say later, is conservative, we can calculate forces applied on this molecule using a negative gradient of this potential. As we can see, these two equations couple into this one, and we will later use this relation to calculate for calculation in our model. So we will need acceleration. Okay, so let's go forward with building this model. Let's assume this is our simulation box, and we put some atoms in it. That will be a gas molecule or gas atoms of, let's say, argon gas. And we will let this system evolve in time. So all of these atoms will change the positions, and we will remember these positions. And if we remember like the initial positions and positions when this atom came from, we can calculate as well velocities. These positions and velocities will serve later on as an input for our molecular dynamics cycle. As these atoms see each other, they will apply a force to each other. So atom 1 will force atom 2 and vice versa. And this will create some interatomic potential. So the next step, or as we said before, we want to use this negative gradient of a potential to calculate the acceleration. We need to define this potential or field or force field or potential energy function. We have two options to do it. So first one will be to calculate the forces without using parameters, but using DFT theory. As was Doa speaking several minutes ago, and this is called ab initio molecular dynamics. But in my case, what I want to present today, we'll be using tabulated force fields, tabulated potentials, and this is referred as classical molecular dynamics. These tabulated force fields are divided in the two categories. So for non-bonded interactions, where we have these atoms like van der Waals forces or Coulomb potential, for example, and then bonded interaction where atoms are bonded, like ionic bond and covalent forces. Basically, what we do in the simulation, we'll choose one of them or maybe both of them and create our potential function. So this is a step 2 of building our model. Yeah, so these were the non-bonded interaction. Let's talk about them more. So for example, we will use a Lennard-Jones potential, right? We have some repulsive part, attractive part, and basically this is the potential function which will be unique for each atom. So if we use I don't know, oxygen atom or hydrogen atom, these parameters of say epsilon, of a parameter of the potential will change from atom to atom. So we'll use like these parameters to create these potentials. What is another important thing I want to show on this slide is the range for which we let this potential to apply. At some point we'll cut it because you'll see like it's close to 0 and it will be really time consuming and memory CPU consuming in order to perform a computer simulation. So we decided to cut it at some point. I will speak about it later. As well, we can use a Coulomb potential, but it depends on the system we are modeling, right? So this is an example for non-bonded interactions. Another example will be for bonded interactions. This is basically the potential, intermolecular potential, or the forces which are holding each biological molecule together. And now we need to count with them. So we need to count with the forces for bonds. We need to count with another forces for bending angles and the torsion forces. So, okay, this was the step 2, and let's take a look how this molecular dynamic cycle looks like. So we start with some initial position of positions and velocities. Then we introduce intramolecular potential. Then we will calculate the forces on this molecule using the negative gradient of this potential, and eventually we will solve Newton's equation when we get this acceleration. So basically we will move from time 0, and we will make one step, and we will get the time dt. This is considered as a one time step, and this numerical integration is purely domain of the computers, and this will be like the third part of our building of our model. So how we will use this acceleration to compute like the next steps in this cycle. We said we want to get from first initial position to some position in the time. Use acceleration. So basically, we will take a look on the position vector or the velocity as we have it from the beginning, and we make them evolve forward in time. And for that, we use a Taylor series expansion. So the first derivative of the position vector will be the velocity, and from the velocity it will be acceleration and etc. Is it important here to mention these time steps need to be on the scale of the system we are looking for. So if we are looking for some vibrational motion, let's say, our time scale needs to be shorter than this vibrational time. It's typically for molecular dynamics in the range of femtoseconds. So we want to move a next step using the acceleration. For that, we will use computer algorithm because this is a set of many differential equations, and like it's not possible to do it by our own. So we will use a computer algorithm, for example, this Verlet algorithm. When we make a next step in a position and one step forward and one step backward, we will do this Taylor expansion. So from the position to velocities, the second cubed term, not second square term will be the acceleration, then will be some cubed term, which is not important right now. And we will end, we will start stop this expansion at dt into the power of 4, and this is basically the error we are doing in this expansion. As we do this expansion again in the forward and backwards in time, we'll see, and then we calculate, we count these two equations together. We will see that we described the next position, t plus delta t, the next step by the current step, r time t, and the previous one and the acceleration. And we are making the error of the power of 4. Yes, oh, I forgot to show it. Yes, so these velocities will go out and these cubed terms will go out as well. As we see, we lost the velocities performing this Verlet algorithm, but we can calculate them recursively from this equation. So if we make this Taylor expansion only to the second term, so we stop this expansion here, we can calculate the velocity of in time t from a previous and the next step, as well with the error of t squared, dt squared. Okay, this is not an easy task as well, and it comes with a lot of limitation for itself. So let's talk about them. If you have some simulation box filled with atoms like this, and we want to calculate all of these pairs interacting to each other, we will be creating very long list of these pairs, and this can result in really long time and memory problems for our algorithm or computer. So we start to develop new strategies how to make this time shorter. So another strategy is self-subdivision, and we divide our simulation box to the cells which are in the size of RC. It was basically this range where we cut our potential, so we will not see over this RC distance, and we will make this subdivision a bit bigger. So basically, one molecule in one box can only see another molecule in the same box or in the one box which is next to each other. So we reduce this listing, or we can this more another advantage. We can list it only as a neighbor list, which will take only the atoms for this list in the range of diameter of this RC plus and delta R. So these steps will dramatically reduce our computational time. Another strategy is to make it easier is to freeze high frequency motions by applying distance constraints to the bond length and angles, which will result in the larger time steps. Or we can use a different time steps for evaluating different motions, or we can join several atoms into a single interaction site, like methane, for example. Next limitation is about the surfaces effect. So let's consider 1,000 atoms arranged into 10 by 10 by 10 cube, and we see nearly half of these atoms on the outer faces will be on the outer faces, and these will have a large effect on the measured properties. So how we can avoid this? We will introduce periodic boundary conditions, where we basically create a copy of this simulation box and replace it to each side and 1 over. So, and this result in two things. Like if an atom will go out of this simulation box, it's immediately replaced with this copy from another simulation box. So we are not losing atoms. And second thing is, if this atom was in the edge of this simulation box and has no interaction with other items, now we'll have an interaction with its copies from adjacent simulation boxes. So that's enough about the building building a model and of our molecular dynamic simulation. Let's talk about the outputs we can get from it. So we can, for example, compute thermodynamic properties like temperature, pressure, and heat capacity, but for us, it's more important our structure properties, like, for example, radial distribution function. As you remember, was mentioned by the talk of Moritz in February this year in scattering theory 3, I guess. So we can calculate this radial distribution function for monatomic, polyatomic system, or even we can calculate static structure factor, which we basically measure in neutron experiments and compare it to our neutron data. Next, very important thing where field where these molecular dynamics is to calculate dynamic properties. For example, the time-dependent radial distribution function. So we get this function directly from molecular dynamics. And if we do the special Fourier transform, we'll get the intermediate scattering function, which we can measure here in Ireland in Spinnaker on WASP on IN15. And then we'll do again that another time Fourier transform, and we get the dynamic structure factor, which we measure on inelastic neutron experiments. So basically, I don't want to talk about this. It was mentioned before. These equations are known. As well, we can calculate the diffusion coefficients or vibrational density of states. But we will not do it by hand. For sure, we will use some kind of software. The software is called MDANSE. And basically, it's a free software. Basically, what the software takes is an input in the form of trajectory we compute from a MD simulation. And the output is, again, the thermodynamic properties, structure properties, or dynamic properties. As an example, here I'm showing the carbon nanotube with a solution of water where I calculated vibrational density of states. So this will be for the molecular dynamic part. Let's take a look on the Monte Carlo on the second topic of this presentation. So Monte Carlo simulation. Here we use a law of large numbers, which says if we perform the same experiment, the same condition very many times, eventually we should converge to some value or some. If we take an average of all of these results from this experiment, it should converge to the true value of the property we are looking for. Here I'm showing it as an example as the Monte Carlo is working. So let's think about the simulation box in which we have one square with a side A and one circle with radius A. And we will start randomly throw balls into this simulation box. And after a while, this box will be full of the balls. And what we actually did, we sampled the space of this square and of this circle using these balls. And if you know the equations, and if we conserve these sizes, similar, we can calculate by counting the numbers of balls from a circle and from the square. And we can roughly estimate the pi number. This is what the Monte Carlo simulation is about. So it's taking some random steps besides the molecular dynamics. So what is it exactly, and how the algorithm, Monte Carlo algorithm looks like? So it's a similar method to molecular dynamics, but it's using a stochastic sampling of a phase space rather than solving the Newton equations of motion. And after each random step, a new atomic configuration is acquired, resulting in a new potential energy. So this is the difference between Monte Carlo and molecular dynamics. The typical MC Monte Carlo algorithm looks like we create some random atomic configuration. Then we'll compute potential energy difference between this old and the new configuration. And we will decide if this potential energy is lower, difference in this potential energy is lower, then we'll accept this move. And if it's higher than lower than zero, we'll accept this move. If it's higher than zero, we'll accept this move with a probability. And again, then we create another configuration and again compare this potential energy difference. And this will go on and go on. So let's take a look on what's the difference between them, or what they have in common. So these are two ways how to look on the conformational problem. So by molecular dynamics, we are let our structure evolve in time by integration of Newton equations of motion, and then we make an average using ergodic hypothesis. So we make an average of ensemble. And by Monte Carlo, we are basically simulating really different, a lot of different configurations, which based on this criterion should converge to the same configuration. And we can say that if our system in molecular dynamics was evolved into equilibrium, we can say like this: these two, the average is equal. Second example is how to look on it as a sampling of a phase space. So as we see, we are creating some kind of trajectory using molecular dynamics. Monte Carlo is using a random sampling. It has its own advantages and disadvantages. So if we use Monte Carlo, we can sample a larger phase space. So there are some regions where the molecular dynamics can get, or we can have a trouble. We can stuck with our molecular dynamic trajectory here and don't get out of it, for example, or here if this potential barrier is too big. Let's take a look on some examples for reverse Monte Carlo. Difference between a reverse and this classical Monte Carlo is that by reverse, we are not approximating, we're not trying to get to some minimum of potential energy, but we are approximating data we got from experiment. And by doing this approximation, we'll get like configuration of our atoms, which should be in agreement with the experiments then. The first example is the results, comparison of the results from the Monte Carlo RMC, reverse Monte Carlo and molecular dynamics simulation. You can see for metallic glasses. And we can see they are pretty good in agreement. And the next example is this reverse Monte Carlo was used for the data of structure factor acquired by neutron or X-ray scattering. So we can see as well this Monte Carlo simulation is pretty accurate for simulating it. The last thing I want to show you, this is a simulation of entire experiment or virtual experiments. So where we basically take both of these methods, Monte Carlo and molecular dynamics. By using Monte Carlo, we will simulate our instrument by means of composing some components. We will do it in this program called McStas. It's as well free software. And what we do there is we basically construct our experiment, our apparature by, we see the neutron guide, some chopper, some monitor, monochromator, etc. So this will be simulated by Monte Carlo. And then we'll use our input of the trajectory from a molecular dynamics simulation. what can this gives us is like the better control of our experiment, because we can control all of these parameters, and this is an example of how this simulation looks like. So we can then decompose the total signal to coherent, incoherent, and even for a multiple scattering from cryostat and containment. Yes, and this is basically it. And yes, I would like to finish with some take-home message. So molecular dynamic simulations compute the trajectories of atoms or molecules inside materials. From this trajectory, we can calculate thermodynamic, structural, and dynamic properties. And Monte Carlo is a powerful tool using random sampling of a phase space for dealing with problems that cannot be solved analytically. And here I would like to say thank you for experts Miguel, Eza, and Stefan, and they helped me with this presentation, as well to my supervisor Marek, and of course to Dua. And in the end, I'm showing some references which I used for creating this presentation. And yeah, thank you for your attention.